I hate to interrupt the great conversations at the tables, but I will. We're going to get started with our program. So good afternoon, and please join me in welcoming our webcast viewers. Thanks for being with us. My name is Andrew Graham, and I'm the President-elect of the Canadian Club of Toronto and your host. We're proud of the club's track record for providing a forum for decision makers and thought leaders to share their viewpoints with us. Normally we have a lot of business speakers and political speakers, and it's a real treat for us today to have someone who is so eminent in their own field and give us a bit of variety, frankly, from the politicians and business leaders that we normally have on stage. But before I formally introduce them, let me tell you about some of our upcoming events. On Tuesday of next week, we have Anthony Lacavera, founder and chairman Global Live, and now author. He'll be joining us to talk about his new book and why business as usual is no longer an option. And on Friday, October 13th, we feature perspectives on the Canadian banking industry, featuring leading bank representatives discussing innovation, compliance, new technologies, and their planned trajectory for success. To order your tickets or to learn more about the club, please visit our website, canadianclub.org. You can also join the conversation via Twitter and Instagram by following us at CDNCLUBTTO. Might have had an extra T in there. You can find the proper hashtag and Twitter handle on your table. It's on everyone's table right in front of you there. I would certainly invite you to connect. And I want to express special thanks for today's sponsor, Queen's University, represented here by Don Raymond, for your generous support. I also want to acknowledge the youth and young leaders who are with us today from Runnymede Collegiate Institute and the University of Toronto's Physics Department. So, thank you. And remember, if you have a question, please fill it out once the Q&A cards come around and at your tables, and one of our staff will collect it. In fact, the Q&A cards, I think, are there already. If you filled it out, just signal, and one of our staff will collect it. And now on to our guest speaker. Simply explained, physics studies matter, energy, and how they interact. Physics and astrophysics are obviously very important topics any day of the year, and we were reminded of that very recently, of course, with the mesmerizing solar eclipse that took place just a few weeks ago. We're paying closer attention to our physical environment and how matter and energy interact with it. So who better to explain why physics and astrophysics are so important than a Nobel laureate? 2 years ago, Canadians were justifiably proud that a member of our scientific community had been recognized with one of the most sought-after prizes in the world, the Nobel Prize in Physics. And I was asking our speaker today whether getting a Nobel Prize was life-changing, given that he'd already received so many awards, right? This is a very well-recognized person even before receiving the Nobel Prize. And he told me that he gets now, on average, one speaking invitation every day. So I think it just shows again how fortunate we are to have him here with us. Queen's University Professor Emeritus Dr. Arthur B. McDonald had already amassed an impressively long list of prizes before the call from the Nobel Prize Committee in 2015. Among them, the Companion of the Order of Canada, 12 honorary degrees, and a Lifetime Achievement Award. For more than 25 years, he has directed the Sudbury Neutrino Observatory Scientific Collaboration. The Nova Scotia native has also been affiliated with Queen's since 1989. He's a renowned expert in the tiny and elusive particle called the neutrino. And in preparing for today's talk, I did what any one who's not a scientist and who grew up listening to CBC radio would do, which is that I went back and listened to some old Quirks and Quarks episodes. And what I was really struck by were some of the episodes right around the time the win was announced. And Bob McDonald, the host, of course, talked about why the Nobel Prize was so meaningful and some of the research around neutrinos. But I was really struck by what he said about Dr. McDonald as a person. He said, not only is he knowledgeable, he's generous with his knowledge, he's gracious, and he's a gentleman. I can't think of anyone more deserving of the Nobel Prize. We're delighted, Professor McDonald, that you're here to explain why science and innovation make for a fundamental partnership. Dr. McDonald, the Canadian Club of Toronto's podium is yours.
But as they say, enough about me. So I'm going to talk to you today about our projects in Sudbury, which started with the Sudbury Neutrino Observatory, really starting back in 1984, and now is proceeding with a major international underground laboratory, Snow Lab. They are both 2 kilometers underground. You can see on the left of that figure the size of the CN Tower compared to how far we are underground. And we are way down there, and the reason is that if we didn't, our detectors would glow like the Northern Lights for the same sort of reasons. The cosmic rays that cause the atmosphere to glow would make it impossible for us to do what we did with the Sudbury Neutrino Observatory, which is to observe 1 faint burst of light an hour from neutrinos from the sun. What you see along the bottom of that figure is a representation of the Earth and things larger than the Earth, the solar system, Milky Way galaxy, and the local supercluster. With these measurements, we're able to study not only the sun, which is mainly what I'll talk to you about, but also the particles that are the most microscopic that we know, neutrinos. And in addition, we are able to, in the future, with a detector with a renovation of the snow detector, we're able to study neutrinos from the Earth, which will teach us geophysics, the way in which heat flows in the Earth. We're able to study our Milky Way galaxy. When you look out on a starry night, you may be surprised to find that there actually is 5 times as much matter between the stars that does not glow as there is in the glowing stars themselves. They're particles that we refer to as dark matter particles. We know they're there because otherwise the stars that are on the outer reaches of our galaxy are going so fast that they couldn't be held in the paths that they're traveling because there wouldn't be enough gravity. And so there's 5 times as much mass in between the stars as there is in the stars themselves. We know these particles are going through us at the present time. They'll bang into our detectors in this new Snow Lab facility, and we'll be able to observe them. No one has ever seen these particles before. They're outside our experience in the world of physics. People are trying to create them. Scientists from Canada are trying to create them at the Large Hadron Collider in CERN with the idea that there may not have been enough energy up till now to create the mass necessary for these particles. But we are in a very cooperative set of measurements in our underground laboratory here in Canada in terms of sensitivity. So we study the world from its most microscopic to its largest reaches with this facility. So we understand on the basis of our measurements how stars burn. We now have a very accurate measure of the nuclear reactions that power the sun. We study the basic laws of physics. We have changed our ideas on how neutrinos fit into those laws, and that's really the reason for the Nobel Prize having been awarded to a large number of people who were in our collaboration, but one person receives it, and I'll show you a little bit about them later on. And we also study the composition of our universe. These dark matter particles are unknown. We hope to know more about them. Neutrinos are unusual things. They're outside your experience. But right now, there are millions of them going through you, created in the furnace that powers the sun. If you hold your thumbnail out, that's about a square centimeter. Count to 3, 15 million neutrinos have gone through that thumbnail during the time you're counting. Once in your lifetime, 1 neutrino will change 1 atom into something else, and you won't even notice it. Unless it happens to hit you in your eye, and your eye is closed, as they often are by the time I get to this point in my talks, then you might possibly see a little burst of light that represents that neutrino interaction. And it's those little bursts of light that we had to prepare for in trying to do our experiment. Neutrinos are very fundamental. Along with electrons and quarks, we don't know how to subdivide them any further. They come in 3 flavors. We'll never taste them, but that's the term we use. We physicists love these sorts of whimsical terms. In the standard model that you heard a lot about when the Higgs particle was discovered, again with Canadians participating, the prediction was that neutrinos had 0 mass and that they never changed from one of the flavors to the other. They're unusual particles because they only feel one of the forces of nature, the weakest of them. And therefore, they can penetrate through almost anything. That's wonderful when you're trying to get them out of the core of the sun and understand how the sun burns. But it makes them very difficult to detect. They can go through the distance that light travels in a year of lead, which is 100,000 billion kilometers, with only a 50% chance of hitting something. So we had a detector the size of a 10-story building with an ideal material, heavy water from Canada's reserves, to observe 1 neutrino per hour in this measurement. We were actually able to observe that they did change from one flavor to another, and that is the revolutionary thing that requires the theorists to go back to the drawing boards and attempt to incorporate them into the standard model. When we started out in 1984 to try to answer this question with our founders, George Ewan from Queens and Herb Chen from University of California at Irvine, and I emphasize this has been an international project from day one, with Canada having a major role in it. There were measurements had been made of neutrinos from the sun, of the type of neutrinos produced in the sun. There are only electron neutrinos produced there. And too few were observed by factors of 3 or more. So either the calculations of how the sun burns, which is pretty fundamental to our understanding of physics, either they were wrong, or perhaps those electron neutrinos were going against the standard model and changing into other types. With heavy water, we could measure both the type that's produced in the core of the sun and separately all neutrino types. A comparison of those two is independent of how many left the sun in the first place. You simply look at what fraction of the total is still electron neutrinos. That's what we did, and that was very effective in getting a clear answer to the question. If you look at this graph, the hatched area at the top is the number of neutrinos that were predicted to be produced in the sun. 5 million per square centimeter, per thumbnail if you like, per second. What we observed when we looked at all neutrino types, if you see the blue bar, is that we were in excellent agreement with the solar models. That meant that we understand how the sun burns in great detail, and that's a very valuable thing. However, when we looked at how many were electron neutrinos, we understood why the other experiments were seeing too few. Only 1/3 as many electron neutrinos as the total number. There was less than 1 chance in 10 million that they were not changing from one type to another. That's 5 standard deviations. It's the criterion for, quotes, a discovery in particle physics. And this is back in 2001 and 2002, and it was at that time lauded as a major discovery. And the theorists had to go back to the drawing boards. This is how we did it. As I said, we built a detector the size of a 10-story building, 2 kilometers underground, 34 meters high, 22 meters in diameter. In the center was 1,000 tons of heavy water, loaned to us from Canada's reserves. Heavy water is used to slow down neutrons without capturing them in the CANDU nuclear reactors. It's a naturally occurring substance. The water on your table has 1 in 6,000 heavier molecules than H2O. D2O has an extra neutron in the nucleus. That's what made it possible for us to observe these 2 reactions. That was housed in an enormous 12-meter diameter acrylic sphere, 5 centimeters thick, which had to be put together out of 120 pieces that were small enough to come down in the mine cage to reach our level. That was done. We constructed it all under ultra-clean conditions. We had 10,000 light sensors that were, someone calculated, capable of observing a candle on the moon if you didn't have any other background light, that sensitive. Single photon of light with a 25% probability. Surrounding all of this was an ultra-pure water environment inside a liner made to keep the radon out, as you'd like to do in your basements as well. And so we were able to get the radioactivity levels down to the point that we had 1 radioactive decay per day per ton of water in the center of the detector. That's about 1 billion times purer than the water that's on your table in terms of radioactivity. With that, we were able to make these measurements, but doing it, constructing it, was a major engineering process as well, and that's science and engineering goes together very well, as it did in this case. Everybody took a shower, lint-free clothing. The conditions in the laboratory as we were building this, even though it's in one of, at the time, Inco and now Vale's most active mines, were ultra clean. You can see the efforts to put together the construction of the acrylic on the left, and you can see some of the workers there in the process. We had a very wonderful visitor. Stephen Hawking has visited us twice, very interested in what we're doing. Absolutely amazing individual. Finding a word for the next word in the sentence. When he first came by clicking a small clicker in his hand, when he came the second time by twitching his right cheek, because that's the only thing he could move. He found the words to ask questions of our students, and he's got a great sense of humor as well. He was talking about the so-called cosmic microwave background radiation that has cooled off to about 2 degrees above absolute zero, or as he said, almost as cold as Sudbury in the wintertime. That someone with his condition can also be very productive and also have a good sense of humor is just an inspiring thing, and it was for all of us. We developed a lot of technology. That was the largest cavity ever dug at that depth. Vale is using it for their work, now down at 2.4 kilometers in the mine, a very productive mine. That water purification technique is being used for other systems, creating computer chips without flaws because the radioactivity doesn't affect them. We were on the internet throughout, pushing the boundaries of internet communication. We were able to control our experiment from a large distance throughout the project. I'm not sure if you know, but WWW was invented by particle physicists at the laboratory at CERN in order to be able to communicate, and we did that very effectively with the use of that. That development of that acrylic sphere, I was in Copenhagen looking at the aquarium that was built there. Everybody else was looking at the fish. I was looking at how well the bonds were made in the acrylic. There's a variety of things, not least the pioneering techniques for an array of low radioactivity measurements. Why should you care? What is it about these neutrinos that's of interest to you? Well, it turns out that your very composition, your history, comes from stars like the sun, where carbon, nitrogen, and oxygen are produced either in the stars or in subsequent supernova. You can actually predict, within about a factor of 2, the natural abundance that's observed for all the elements up to iron by going through the set of nuclear reactions that take place in these stars. We really have a DNA in the elements themselves of what our history, of what our origins have been. A very fundamental topic in terms of understanding the history of the universe. We understand fusion power in the core of the sun held in place by gravity with great accuracy now. The physics we know. Now, here on Earth, we're attempting with tokamak development, for example, to try to harness that 15 million degree heat with a bottle that uses magnetic fields to turn the charged particles back in without scraping the walls that obviously would evaporate. It's an engineering question predominantly. The physics is understood extremely well. And neutrinos are really particles that influence how our universe evolves. And that's very important, as is the dark matter I mentioned. In fact, we think that we're about 4% of the total mass of the universe, that 26% or so is these dark matter particles I'm talking about, and about 70% is something called dark energy, which was discovered a few years ago. It's a modification of Einstein's laws of gravity. You learned in school that gravity is always attractive between a couple of masses. It turns out there's a small repulsive term as well, which only shows up when you measure things at a very large distance. So we understand our universe, we say. We understand what the components are, but in a wonderful Donald Rumsfeld sense, we still have a lot of known unknowns that we have to try to deal with here. And in particular, we want to know what those dark matter particles are. And as I said earlier, we're trying to observe them in our new laboratory, and the other scientists are attempting to create them for the first time at the Large Hadron Collider. In addition to the snow area, which you see on the left of this figure, there's a new area which has been expanded with wonderful support. We have throughout this project had support from the universities, from the provincial, from the federal governments, and international contributions as well. In this case, it's a Canadian development of this laboratory. In that area, it's part of a program from CFI to try to attract international experiments to Canada, and that's been very successful. We have cutting-edge measurements of the most sensitivity available in several different technologies to try to observe dark matter in particular. The Super CDMS experiment you see there is a $35 million US experiment, which won the competition. 2 experiments are being done. One of them is to be sited at Snow Lab. It also has a very good local economic multiplier. The expenditures that are made in Ontario and in Sudbury have a multiplier of about a factor of 3 in terms of economic activity here in Canada. These are the people who really did it. As I say, one person gets the Nobel Prize, but these are the ones who did it. And I want to have their names up there always when I give a talk, because they're the real contributors. But I had available their emails, and I decided I would do a little survey because I just thought you'd be interested in what they're now doing. I mean, this generally we finished in 2006. The students and postdocs are now in long-term jobs. Only 26% of them are university professors, which might be what you might expect, and maybe what they had in mind when they started out doing fundamental research. A number of them own their own companies. Membritech, for example, uses the water purification techniques that we had developed to provide systems for small communities, basically turnkey systems that use the reverse osmosis process. There are also technical leads in a number of prominent companies, as you can see there. 26% of them work in major research laboratories in medicine, physics, geophysics, and a variety of the ones in Canada and the US. 15% are in government. CMHC, National Defence, Natural Resources, in the UK, Business and Security. And a number are actually in finance. We were discussing that a little bit at the table here. You can see they're working for well-known companies. Really, 75% or so of the people who are trained in fundamental research have learned how to answer a question by following a research topic to its conclusion. They end up as very valuable people in industry, in government, and in our society in general. And that leads me to talking about what has come to be known as the Naylor Report, because David Naylor, as the chairman, did such a wonderful job on the federal panel for fundamental science, which I also participated in over the last year. A report was put forward in April, and it dealt with all of the funding system of Canada. The reason why it's important is that whereas Canada has been doing extremely well in the past, we're slipping, to put it simply. The research competitiveness has been eroded, particularly over the last 10 years or so. You can see in the upper graph the total funding per researcher from the various granting councils for people who are individual researchers pursuing topics that are following the cutting edge in fundamental science. The federal government contribution to what has been a reasonably robust total investment in higher education research and development has declined. You can see that blue curve and the way it's tailed off in recent years. And it's only 23% of the total. That dashed gray line is what the universities themselves put into this exercise at universities. There's a problem, and that's what our report identified. If you look at the gross expenditures on research and development in general by Canada, this is a plot of, for example, the top 10 people in the OECD, top 10 countries in the OECD. You can see where Canada ranks and where it's going. Similarly, in the G8, we are not pulling our weight internationally in terms of gross expenditures on research and development. And in direct project funding, there really has been a lot of pressure in the last 10 years because the new initiatives, by and large, in project funding at the granting councils have been directed to top-down prioritized initiatives that, by and large, are aimed at commercialization. And that's not something we think is an inappropriate way to spend money. We think it's very important for Canada to continue to be focusing on innovation. The point we're trying to make in our report is that if you don't have a robust fundamental science base, then you are not going to have successful innovation either, as well as you're not going to be training that set of researchers that I illustrated to you with our SNOW project. The imbalance will greatly affect our ability for innovation, as well as in the social sciences for decision-making that is evidence-based when it comes to a variety of things. For example, how do you deal with reconciliation with our indigenous people? There really needs to be support for the social sciences and not just the natural sciences. To show you the sort of situation, and it was really difficult for us to listen to the younger generation who are feeling, well, they're discouraged by the fact that if you look at the two red circled upper boxes, the average grant for a researcher is not enough to pay a postdoc. Very difficult across the regime for people to be able to do effective research. And in CIHR, for young people, and we listen to a lot of people, including a lot of young women who are in this young early career researcher cohort in larger numbers than in the past. 14% success rate for applications to the Canadian Institute for Health Research. That is soul-destroying when you come in as a new faculty member and you ask, when are you going to get your first grant? Well, success rate is 14%. Here are some other anecdotal comments. The first one is that there's not enough to afford a postdoc, as I said. If you compare what CIHR spends per citizen compared to the National Institute for Health in the United States, it's about a factor of 3 or more lower. Very difficult for Canada Research Chairs even to have an adequate operating grant, and it really is having its effect on diversity. Our recommendations in the report dealt with governance, oversight, and advice. We're very, very pleased. I was participating in a ceremony on Tuesday on the appointment of a new chief science advisor, and that is something that I think, oh, hey, David. I didn't even notice that you were in the audience. I must introduce David Naylor, who did so much to lead this report, and I'll join in that. The choice of Mona Nemers as a science advisor is something that will be applauded across the community. The fact that the government has followed through on their proposal for a chief science advisor is going to be very valuable. In our report, we proposed a variety of improvements to peer review processes, and also we proposed some agencies that will or coordinating boards that will give us an opportunity to have a continuing oversight on how well we're doing. I've mentioned diversity in early career researchers. We also worried and commented on multidisciplinary research, internationalization, and rapid response for new ideas. But the highest priority, as I said in red at the bottom, is the restoration of funding levels for the granting councils to 2006 levels. Our recommendation is an average of about 9% increase per year for 4 years. That in total would be about 0.4% of the federal budget. It would get us back to the sort of level that we were at in 2006, and hopefully restore Canada's international role, but also all of the things that fundamental science gives you in Canada that I've tried to list here. The evidence for evidence-based decision-making, the next generation of highly qualified personnel and technology leaders, both as they're trained and as they are attracted from other countries. And let me conclude with this. At the turn of the century, Time magazine selected their person of the 20th century. And they selected Albert Einstein to go on their cover. Not because he invented the laser or the computer or the transistor or the GPS, but because all of the technology that really revolutionized our lives in the 20th century came from things that he did in fundamental science around the turn of the previous century. It really is true that if you know how your world works, then you can apply your knowledge to provide things that are better for our lives. In Canada, we're in danger, we feel, and this is the conclusion of our report, of losing the next generation of fundamental researchers who can contribute so much across the spectrum: natural sciences, engineering, health, social sciences, and I have health in there twice. I meant to say social sciences and humanities. We need to reverse this decline in our capability for evidence-based decisions through fundamental research, and we can go back to being a leader in science and innovation. Thank you very much.
Thank you very much, Professor McDonald, for coming to join us and for speaking so eloquently both about what you and your team did and also why science and science policy is so important. So thanks again for that. I think we have time for a few questions. Some are sort of scientific in nature, others are about science policy. Since you've just been speaking about science policy, let me start with one from about that, and really about how do we encourage more women to take up physics careers?
Well, I think one of the things that is important is that and we emphasize this in our comments on the funding, is the opportunities that an early career researcher can get into the activity of fundamental research. Because, as I said, our cohort that is now beginning has a much larger fraction of women. It's different across the different disciplines. In medicine, I understand at Queen's about 55% of our people studying medicine are women. In physics, it's maybe 10% or something like that, and it declines in the upper years. So I think opportunities in the early career and then opportunities within the university for progression, consideration for special circumstances for women, such as the opportunity to have a family and still be able to proceed with their research careers, is very important in the system, and we addressed that in some of our other recommendations.
Okay, thank you. Well, let's switch to more of a pure science question, if I can call it that. Is there any hope of using neutrinos for practical purposes like radio signals?
No, because I think you'd have a lot of trouble with a detector the size of a 10-story building in your back pocket to try to pick them up. So no, that's not really the way in which we use them. We use them to learn other things. We've now learned, as I said, how the sun burns extremely well, which will be helpful in fusion power here on Earth. We also can use them for astronomy. It's a whole new field of studying the largest distances in the universe and the events that are happening there, because they can go through virtually anything. And so, for example, the ice cap at the South Pole is instrumented with a 1 kilometer cube detector that studies the highest energy neutrinos and the highest energy particles in the world, and they are produced in very, very large events like black holes at the far distance reaches of the universe. But I don't think we're going to find neutrinos used in the next generation of cell phones, for example.
Well, I think we'll finish off here with one more sort of science policy question, and I think you've certainly addressed part of it in your talk about the importance of science and the slipping of Canada versus other countries. But maybe you could talk a bit more about how important you think it is that there's leadership for Canada, specifically in photonics, which obviously was an important part of why you were recognized for the Nobel Prize.
Well, photonics is something that Canada has been very good at, and there are a number of areas that Canada needs to be emphasizing as we go forward. Another thing that has received publicity recently is artificial intelligence, and Jeff Hinton at the University of Toronto is a world-acknowledged expert. I was at the National Academy of Sciences last May. The head of Facebook, the head of Google, gave talks about the directions they're taking. They both specifically mentioned Jeff Hinton as as a person who has made significant contributions from that point of view, and he did it on standard grants from the same granting councils that I'm referring to before he made the breakthroughs that have now been, I mean, my phone recognizes me when I pick it up. These sorts of facial and sound recognitions are fantastic. And also, I think the ability to go forward with quantum computing, but quantum devices, in some cases involving photonics, that's being developed at a number of universities across the country, but with a real focus in the Waterloo area, is something that Canada can excel at as well. So there's a number of areas that we're poised to do extremely well.
Great. Well, thank you once again.
Thank you.
before we get to our formal thank you, I wanted to recognize mediaevents.ca, Canada's online event space, and VVC for live streaming today's event. You'll find this address, as well as photos and videos of many of our past events at our website, canadianclub.org. Without further ado, I'd like to welcome the Chancellor of Queen's, Jim Leach, to take the podium. Thank you, Jim.
Thanks very much, Andrew. And as Andrew said, I have the pleasure of serving as the 14th Chancellor in the 176-year history of Queen's University. So I want to thank the Canadian Club for hosting this great alumni event today. And of course, one of our most illustrious alumni, a Nobel laureate and a research leader, Art McDonald. He heads a team, and there are many at the university of researchers who are pushing the boundaries of knowledge and tackling some of the biggest questions we have. I remember vividly in the 1980s being a young board member at Queen's when we approved a very small initial grant to build a big hole in Sudbury. Had no idea what we were doing, but look how it's paid off. I would say one of the proudest moments that I've had was in October 2015 when it was announced and we heard the remarkable news of the Nobel Prize win. Now, I happen to be a physics grad myself, and for those of you who didn't get the whole neutrino story, the easiest thing to do is to Google Rick Mercer and neutrinos, and you'll see a video of Art explaining the difference between neutrinos and Timbits. It's quite enlightening. We're so proud of Dr. McDonald and proud of our university, and most importantly, proud of Canada. This was the first Nobel Prize since 1994 for Canadian-based STEM research. I want to thank Dr. McDonald for speaking to us today and telling us the story and the background of that research. It's truly a Canadian story as well as an international story, a story that shows the possibility when academic institutions, government, and the private sector come together in partnership with a shared vision. And it's a story that underscores the importance of fundamental research to Ontario and to Canada, a subject that Art is most passionate about, as you heard, and he advocates for, and let's hope people are heeding his warnings. I'd also like to thank Dr. McDonald for being a tireless ambassador for science and for Canada as he travels around the world and all the speaking engagements he does. Recently, he was in Italy to announce the formation of the Global Argon Dark Matter Collaboration, which is a partnership of 350 scientists from 68 institutions in 12 countries, searching for the mysterious and elusive dark matter. It's through those international research partnerships, brilliant minds in Canada and around the world are advancing our understanding of the universe and setting the path for new directions to be studied in chemistry and astronomy. And again, thank you very much to the Canadian Club for hosting us today, and in particular for giving us the opportunity to hear directly from Art McDonald, our most recent Nobel laureate. Thank you.